Hello and welcome back to Calculus 3. So we're starting chapter 14. We're going to talk about vector calculus. We're going to first learn about vector fields and then transition into line integrals, then do some conservative vector fields, then jump back into Green's theorem, which is more line integrals. So it's going to be back and forth. So before you start looking at definitions and mathematical constructs over here, let's first understand what vector field is. I am very happy to see that fan in the back, because that fan is generating a vector field. What you are supposed to imagine looking at that fan right now is infinitely many little vector arrows pushing in the way the air pushes. So the propeller on that fan forces the air to move forward, and that force of motion, the wind which is creating, that wind is an example of a vector field. So you are thinking of a three-dimensional space that it's filled with little vectors. They're all pushing in a direction. They don't have to push in the same direction. They don't have to push with the same strength. But there is some mathematical, and we'll see what, some mathematical structure that can describe that kind of motion. So, great, wind, right? What else? Water. You open the faucet, right, and the water rushes. Or even better, if you take showers, right, that's also the vector field. The water molecules are pushing the way they push. But we generally use fields to understand electric field, gravitational field, magnetic field, and all other fields out there. And each one of those is a vector field because we can find the direction in which it goes, right? And we describe, positive, negative for electric field, north and south for a magnetic field. I mean, they are unified, but still, right? We differentiate between them. And then gravitational field, and then there are other fields that exist. So currently, looking at the latest from physics, we know that all of the fields that exist and create the mass and everything else. So now, the field is simply whole bunch of arrows in a 3D space pushing in the same way. So if I draw over here a fan, right? This fan will get the air going forward, but there's just infinity of these arrows, and they will disperse. Yes, they will disperse. There is a mathematical way. So all of this is a lot of vectors in R3. So we will call that a vector field. Now, a vector field could be a 2D, could be 3D, could be 10D, depends on what you are computing. Also, heat distribution and just technically anything. Anything could be vector field. So we are going to start with a definition of vectors in 2D. So vector fields in 2D. also known as R2, right? So let F and G be defined on a region R in R2, so in two-dimensional space, just X and Y. A vector field so vector field in R2 is a function f. Now you have to be very careful. This f needs the arrow on top because the vector field representation that assigns to each point in R a vector f of xy, g of xy, notation f of xy is equal to f of xy, g of xy. We can also use the ij notation plus g of xy, j. Now these guys are the carets, right? Those are the unit vectors. So when you're looking at this definition, you should immediately ring the bell from your definition of a function. What's the definition of a function? From pre-calculus and then calculus 1. Function is a rule which assigns to each x in the domain a unique y in the range. You see the same definition here, except you are assigning to each point in space R, you are assigning a vector f. So you are not assigning point to a point like you assign in the basic function. Now you are assigning a vector to a point. And each one of the vectors is figured out using these two functions. Now, hopefully you also are connecting and in your head saying hello parametrization, right? Because that's at the end what's happening here. So that's the definition. I will box the formula which will be there over and over and over again. Now we are also going to say over here a vector f, a vector field f which is f and g of x and y, right, is continuous indifferentiable on region R in R2 if f and g are continuous and differentiable on R. Eventually that will play a role, not yet. So let's take a look at some examples of vector field in 2D. Now these ones you can draw and it's time consuming, right? But as many of the things are in this course, right? Carpal tunnel. So let's take a look at few of these examples. They have these ones done in a book. Maybe I can find something else in the homework. If the homework ever opens. Aha. Amen. So they gave you few of the 3 fields in 2D, an example in a text, and now I'm going to work out 2 different examples from homework so you guys can see. So let's start with problem number 12. Let's see. So vector field is given as x plus y, comma, I think y. Yes. All right. So graph, describe, do something with this. Let's go graph. All right. So what do I have? I have a formula for vector field which contains 2 functions in it. Function f, function g. Now I hope you see that this function will generate a vector, that it's 2D vector because I only have 2 components, f and g. So your job now is to pick random points in space and plug them in and see which vector you get. Whatever you get, you draw starting at the point you computed. So here's the XY coordinate system. This is 2D, so that's the, the R2 thing. So what I'm going to do now is I'm going to go and say, okay, I want my input to be 0, 0. I want to see what happens at the origin. Well, nothing happens at the origin because 0, 0 is producing a vector 0, 0. And vector 0, 0 has no magnitude, has no direction, so it's just a dot in the middle of the graph. Then you say, okay, but let me see what's happening at 1, 1. Okay. So before this becomes confusing, you are picking a point that has x and y coordinates. So let's use some common sense. You plug them where they belong, and that will generate a vector. So you're not going to get 1, 1 back. You are going to get 2, 1. So I am supposed to draw a vector 2, 1 emerging from 1, 1. Point 1, 1. So I'm going to draw a vector 2, 1 emerging from point 1, 1. This is point 1, 1, and the vector 2, 1 is this.
Any direction?
I'm sorry?
Any direction of the vector?
The direction is
How do we know that it doesn't go up?
it does go up. It goes up. You mean this way or that way?
Yeah.
Because it's 2, 1. 2 squares.
Oh, yeah.
2 squares this way, 1 square this way.
Yeah.
So it has to be this way. That's 2, 1. So let's pick 1, 0, for instance. If I pick 1, 0, the vector is 1, 0 also. Okay. How about 1 and negative 1? Well, that's going to be 0, negative 1. when you plug them in. So 0, negative 1. I'm sorry? Pick another point. Let's pick 0, negative 1. 0, negative 1 is negative 1, negative 1. So 0, negative 1 is here. I need to go down, left. How about 2, negative 1? If I get a 2, negative 1, 2 minus 1 is 1, and then y is negative 1. So we go here, go 1 unit up, 1 to the left. This is chaotic, right? But it works. So you can go and, you know, compute another 60 points, and you will have much better representation in the field of what's happening with the vector field. But what I want to write here is, yes? It is going down. It's 1 unit. It's going this way. Like this. Right? Good. Good, good, good. So in other words, we assign a 2D vector to each point in R2. So we assign a 2D vector in this case. We're going to do the 3D pretty soon, but I hope you understand that the points is what you pick. So just go back. Your first experience with graphing in algebra was, I give you some x's, you compute y's, then you have x and a y, you plot those, and then you connect the line, right? Like in a coloring book. A little bit different concept because it's more involved, but instead of me giving you an x value and you giving me back the y value, I am giving you both x and a y. You plug those in here and you give me the vector that corresponds to that point. And at every point, you might have a different vector, this was a good example to see. You don't have to have everything line up nicely. It could go all over the place. So we'll talk about rotational vector field, radial field, and many other things. So as long as you are grasping the idea that you pick the point 0, 0, 1, 1, negative 1, negative 1, 1, 0, 0, 1. So you are picking the points, and to each point that you pick, you will be able to compute the vector that is supposed to emerge from that point, the point you picked. A very good exercise is to match the field to the given formula. So you're looking at this, you're looking at the formulas up there. Look at this one. What does this remind you of? A road. Okay, we can think about the road, and where are the cars moving fastest? Where are the cars moving slowest? Left in the middle. I'm sorry?
Faster in the middle.
Faster on the outside. Short arrows, right? Short arrows. Short arrows is this. That's short arrows. Longer arrows, right? So more force, more speed, more everything, right? Longer arrows, more. Shorter arrows, less. So if you want to look at that as the wind, you can. Flow of the liquid, you can. We want to actually see the flow of the liquid completely opposite. We want to see the long arrows in the middle and the short arrows at the edges, because the liquid, when the liquid is in the vessel, like blood, or you have water in a hose, or you have the river in the riverbed, right? As it flows, there is friction between the liquid on the outside and the edges, and the one in the middle pushes more. I think the example in the book is actually the flow. So this would be the well, it's not anti-flow, but it's actually the road, where we know that people generally speed on the outer lanes rather than the middle one, right? In the middle one, you realize, like, who's gonna let me out first, right? It's the middle one. So yeah. Now the question is, which one of these, A, B, C, D, which one of these would produce this vector field?
A.
A. The smaller the input on X, the shorter the arrow. The larger the input, when input is 2, 1, 2, when input is 2, 2 squared is 4. Right? So that last one corresponds to A. And you see that B is very similar to what we did X plus Y, comma Y, and they have X minus Y, comma X. So yeah, you should match these. It's very easy to match. You just compute few points and you see what matches that, and that's that. So the idea is to see these vector fields like that. So you draw vector fields by doing the middle school thing. You pick a point in space, say 1, 1. You take the coordinates x equal 1, y equal 1. You plug them in whatever vector field, and that spits out a vector. Let's say 0, negative 1. You draw 0, negative 1 vector emerging from point 1, 1. And you just create these vector fields. You do the assignments 1 to 1, right? And that's that. Examples of the flow, as I mentioned, 1 minus y squared, comma 0. Gives you the horizontal flow. You see that the middle is pushing the most, and the edges are pushing less. So less force here because there is friction, right? There is friction on those. So that's the way to connect physical reality with what you guys are trying to see. And what is the one on the right? It's hurricane, exactly. It's either a hurricane or tornado or whatever is rotational, right? That's what it is. I think they actually have a nicer picture somewhere in here. There it is. See that? So this is mathematical. This is mathematical model. This is what Mathematica, my MATLAB, spits out as the answer, right? And then we dress it nicer and put it on the news and scare people. So, you know, that's that. But you can see the vector field, and then you can see more vector field, and you can see more vector field, which goes everywhere, right? So all of these have mathematical models that connect. You see also some flow of heat in the middle, and then the magnetic field at the picture to the right. Okay, let's now take a look at some important vector fields. So one of those is going to be radial vector field. Radial vector field. So a radial vector field is 0 at the origin, and in general we say r equals xy, and then radial vector field f is going to be given as xy divided by magnitude of r to some exponent. What would this look like? Simply looks like this. Actually, let's do different color. Would this remind you of, let's say, a two-dimensional sun that shines the energy, right? So yeah, why not? You can have the radiation, right, move away in the radial fashion. Now, guys, there are vectors everywhere, right? Every single gap gets to be filled. This is not just 8 vectors that, you know, going around that I drew. This is infinitely many vectors filling in all of the space, all of it. We just put few on our drawing, but there are infinitely many vectors. The next one is the 3D. So now we're talking about R3, which is XYZ. Let F, G, and H be defined on a region D in R3. A vector field in R3 is a function f that assigns to each point D a vector, and now this is very long string here. I'll just put FG age and then you can pick it up from below. So what is the notation? So vector f with the arrow on top. So f of xyz is the vector of f xyz comma g xyz comma age. There we go. Now there's also equivalent form, the one with all the ijk. I'm going to write it, and you can use it if you like it better than the vector notation. So we have f of xy z I with a hat plus g xyz j with a hat plus k xyz. Yeah, supposed to be age in front. Okay, there we go. And immediately vector field VF, vector field F equals FGH without listing all the X, Y, Z's forever. Is continuous and differentiable on a region D in R3 if F, G, and H are continuous and differential. Now let's put diff. And here's the radial. Radial vector field. I'll put VF. I think they have it too. Yeah. So radial vector field is fxyz is equal to, and you have your xyz divided by r. P. I can put P. There we go. Yes, 15th try to put P there. Good. So now that's 3D. Now, obviously, to draw vector fields in 3D is quite a challenge because, right, you are trying to draw a dimensional representation right on 2D surface. So yeah, not fun to do those. But at least we can look at them. I want to start here. If you look all of the motion is going away from the origin. So if that's some kind of source in the middle, then if there's some kind of source in the middle over here, then whatever is radiating out would go that way. And there's your flow. Please note that the arrows in the middle are longer than the arrows that are around the walls. And you see the formula over here that shows the flow of this. Now just, you know, pipelines and blood vessels and I don't know, fuel delivery system in your car, just so much about just that one picture over there. So there are people that are, you know, sitting this, cranking these types of things, and yeah. So I will not be asking you to draw the 3D one, but I might ask you to recognize which one is which, right? Which is, you have those problems to practice at homework, to connect. And now we are going to talk about gradient fields and potential function. Now, let's use our brain power and remember vector valued function. Go back in time. Go back in time 3 months ago. We said that R is f of t, g of t, h of t, right? We said that. So one way to generate the vector field is to not have the parameter there, but instead of a parameter use x and a y, and those would be locations, and you have 3 functions, and that becomes a vector field, right? So the R, the way you look at it right now, because it only depends on t, on a parameter t, that is your vector valued function. It still gives vectors as answers, but it's not a vector field, because you can't really go and pick a position on a 3D space, right, from there. But if you think about having a function to be dependent on x, y, yeah, you are creating the, or x, y, z, you are creating the vector field. Now, think about one more thing here. What happens when I find the gradient of this? Exactly. So now, let me show you one more thing. So I just wanted to connect these things. They're not important, the vectors are not important here. But if I give you a surface, let's say f of xy is equal to 3x squared y minus 6y cubed. I give you this equation. What is this? I mean, I'm not asking you for a shape, but what is this? I said I'm not looking for a shape. This is some kind of a 3D object, right, in space. some kind of 3D object in space. We have the domain as x and a y, and then once I find each location, right, x, y of the domain, I can pass that to the formula. Formula computes z's and attaches them to the points where they created. Now, what happens if I create del f? What do I get? Six xy, that dies, and then for y, nice. We are taking the derivative with respect to y. So we copy 3x squared. That's a constant. The derivative of y is 1. And then minus 6 times 3 is 18. And then y squared. You can generate vector fields like this. So now I'm going to write a sentence which is hidden in your text. I always have to scout for it and scavenge to find it. And it nicely says, a vector field defined as the gradient of a scalar valued function phi is called the gradient field, and the phi is called the potential function. So a vector field as the gradient of a scalar vector phi scalar valued function phi is called the gradient field. And phi is called potential function. So now we can go quickly to notation. So z is equal to phi of x and y. You can add z if you want to. And then we find the del phi, which is a vector. It's a vector field. We have phi x computed at xy, phi y computed at xy, and phi z. Oh no, this is the 2D, so no, that's it. There's also a 3D version of this. Okay. So, two-dimensional version, and in the blue 3D version. Your function, we used to put f of x, y, z. Now we put phi of x, y, z. At least they both begin with f, right? So phi of x, y, z, and when you take the gradient of that, you can generate the field. So our job is to measure the field and try to figure out if there is a function that generates that field. Because if you understand the function that generates the field, you understand the underlying principle of what you're observing and studying. So why would they, put a lot of little probes, right, into tornado, right? What is that going to do? Those little probes are going to send data of their location. And when they send the data of their location, they are recreating the field. And when I have the field, we will see on Wednesday, we will have a method to compute. We will first have to determine the field is conservative and other things, right? That's fine. But if it passes all the checkpoints, we will be able to get the function which creates it. When you have a function, mathematical function for some concept, you understand that concept. You can build it, you can manipulate it, you can control it, you can do a lot of other stuff. So that's what we are looking at right now. So any surface can create the field, and you hopefully know that everything decays at all times due to alpha radiation. So no matter what your shape is, you are potential function which radiates light away, right? So the desks are doing it too, and the computer screen, and this bottle, and everything is decaying at all times, and it's a radial vector field around everyone. So we'll take a short break. When we come back, line integrals.